Okay, we're going to conclude with the connection between continuity and differentiability. So far we've looked at some that had no continuity at point C, such as a hole, or maybe even like that. That's another rendition of that. And then we have the jumps. And then we have asymptotes. All right, so these are three examples of functions that are non-continuous. So if it's not continuous, like these, can we say that it is not differentiable at C? Yes, we can. There's no way I can draw a slope at a spot and draw a tangent. There's no way at these points I can draw a tangent line and get its slope. So therefore, we can say one thing: not continuous implies not differentiable. Alright, so that should make sense. Now, let's talk about it from another direction. Suppose if the function is differentiable at x equals c, what can we say about its continuity? So therefore, if f is differentiable at x equals c, then it is continuous. If f is differentiable at x equals c, then it is also continuous, because we can draw the slopes at tangent points all through the function. Then we know it is continuous all through the function. So we have to put it in brief visual notation. Differentiability implies continuity. So not continuous implies not differentiable. Differentiable implies continuity. All right, can we go any further than that? If it is continuous at x equals c, so if it's continuous at x equals c, must it also be differentiable? All right, if it's continuous at x equals c, must it also be differentiable? Well, just a few examples should cement the answer to that question in your mind. I'll draw you one and then you can tell me if it's yes or no. What if I have that kind of graph? Definitely continuous. I didn't have to lift up my pen when I drew it. So it's continuous at the point C, where x equals c. So must it also be differentiable at that point? And the answer is no. When you have a sharp turn like this, I cannot figure out which way to draw the tangent line, so I cannot get a slope at that point. So the answer is no. So the quick way of saying it is continuity does not imply differentiability. Continuity does not imply differentiability, and this sample would make that clear. All right, so is there any other way I want to go? I think that's good. Here's another tricky one. Here's the sharp turn. But here's another one I do want to call your attention to, and that is the sample where you have y equals the cube root of x. That is a function that comes up and goes like that. So the question is, like right there, if that happens to be our c, notice what happens to the tangent line right there. So we can draw the tangent, but what is the slope of it? A vertical line has no defined slope because you end up doing a rise, an infinite rise divided by 0, an infinite rise divided by a 0 run. So we don't really have a definable slope at that point. Yet that graph is continuous. So this has no derivative at x equals 0. Yet it is continuous. So therefore we can say continuity does not imply differentiability. All right, let me finish up. I want to go back to, that's the ideas for connecting continuity and differentiability. But let's go back to the alternative definition of the derivative. I want to be able to assign problems and have you do them with this alternate definition. So most of the time now we're going to use other methods that are quicker to find derivatives, but I don't want you to get too far away from the limit definition that you forget how to do it. And this, we haven't done an actual problem with this type of limit definition. So let's say the function is f of x equals x squared, I don't know, plus 2, and I want to use c equals 2. So what am I asking? I'm asking for the derivative of this function at c equals 2. If I was thinking about a picture, that is the parabola raised up 2, and I'm thinking about the derivative at 2. So here's 2. I find a picture, I find a point on the graph, and I draw the tangent line, and I get the slope right there. So I want to do that with this definition. So I'm just going to let my nose lead the way, my mathematical nose. So our c in this discussion is 2. So let me write it with a 2 for c. So everywhere there's a c, I'm putting in a 2. So now I can do some of this work. F of x is x squared plus 2. So I've done this, then there's a minus sign, and then f of 2. So that means I'm going to put 2 into this function. So it becomes 2 squared plus 2, and that's all over x minus 2. So right now, if I put the 2 in for x, I find that this denominator zeroes out. So we're hoping that algebraically that will be something I can remove. So let's work in here. I get x squared. Inside of parentheses, I get a 2 squared, which is 4 plus 2. So this whole thing is a 6, and a 2, positive 2, and a minus 6 gives me a minus 4. So now I can say that that's the limit as x approaches 2. Difference of 2 squares, x minus 2, x plus 2, divided by x minus 2, and that's how we deal with that. And I end up then with the limit as x approaches 2 of x plus 2. Now I can put the 2 in without any algebraic problems, and I get a 2 plus 2 or a 4. So that makes sense that this slope of this tangent line is 4. It does look rather steep and positive slope, so 4 makes sense. All right, I just wanted to show you how to use this. You just sort of follow what it says. F of x is given in the problem. F of c, you put c, the number that is given as c, into the function and take the limit using algebra to help you. All right, that's all she wrote for this time, and we will be back together on Monday, and we will do some of these differentiable continuity type problems where we will ask you if this has continuity and differentiability. So till then, have a good rest of your weekend. Till Monday. Bye.